to raise the hand so that I can give you the microphone. So Anirban raises his hand. Yeah.
Yeah, thank you. I had the question to Veronica's talk where she showed that so basically in the hybrid model, so the baryons get suppressed in the high temperature part because of the high mass, isn't it? So how that Polyakov loop comes in the mass part? I mean, what was the modification in the PNGL part so that leads to this if can be answered briefly?
So I wouldn't call it Polycarp loop because, you know, I use it at 0 temperature. It's just an order parameter in the model that using the Polycarp potential that people usually use works very well. And as this is an effective model, but it's a chiral effective model, the masses for the particles come from the interaction with the medium. So if I use the chiral condensate to build this mass, and also an isovector version and a hidden strangeness version. So I also added this field phi in the mass of the particles. And then for the quartz, it goes with a negative sign, so.
Yeah, but what was that phi? Isn't it the Polyakov loop?
I don't think you can call it Polyakov loop. Okay. This is not.
I'm mistaken, sorry.
I would just say it's another parameter for the confinement within this model, but I cannot say it's a Polycarp loop.
I was just trying to understand which kind of modification. Yeah. So you also put some temperature, chemical potential dependence in the potential, right? And yeah, that immediately leads to this kind of modification in the masses. Or
yes, because otherwise,
because I have in mind that the modification which we have seen in yesterday's talk, that some potential in the Dirac matrix itself can give us the modification in kind of a chemical potential change. And I was thinking, so similarly, what kind of modification you have in this version, so that gives you a modification in the mass rather than,
yeah. So if I don't add that modification, if I don't add any chemical potential dependence, I won't have an effect for T equal to 0, and then I want to have an effect for neutron stars. So that was my original idea of putting that there. But as you saw in the talk yesterday, there was already a density independent coefficients that people are using. I just made it more explicit.
Okay.
Thanks for asking.
Thank you.
Yesterday we had a Zoom meeting and I said the most sad sentence on Zoom is "you're on mute," but I was on mute myself now. So I had a question to Jishnu. So you had a comment, so I would just like to know whether it's just an off-the-cuff remark or whether there's something more behind it, that the temperature of the critical endpoint would be lower than the transition temperature in the chiral limit.
Yeah, that is actually, I did not remember the reference, but that is on Fridtjof-Kahr's reference, Fridtjof-Kahr's article on this CPOD conference, from the CPOD.
Okay, so Fridtjof has done. So my question is whether this is an observation or whether it's a constraint coming from somewhere?
I think it's best, sorry. I think it's based on model calculations that when we did the model calculation, they see that the critical point is lower than the chiral transition temperature.
Okay, let's Fridtjof can answer.
Yeah, I guess the figure is actually also on one of Vladimir's slides. It is based on a paper by Hatta and Ikeda, who analyzes the critical line in the vicinity of the tri-critical point in the chiral limit, where you see that the critical line goes out of the tri-critical point just in the way you can decipher it from Vladimir's slides, if you look at it. So it goes, statement is you have the tri-critical endpoint, and the line goes out of this into the direction of even smaller temperatures.
Mm-hmm. Are you there, Vladimir? Or?
Well, Vladimir's back in 10 minutes.
Oh, he's back in 10 minutes.
So he just told me to tell that. So if there's a question,
yeah.
I have a question.
Keep it there around for a while.
Before Vladimir came, the question to the talk about functional renormalization group approach. There we showed Gluon propagator. And it seems that at low energy, small Q square, it approached to 0. It's crucial. 0 or non-zero?
No. I mean, this is the so-called dressing function. So it's the gluon propagator times momentum squared. So this object always goes to 0. I know that, of course, there's a huge debate. Yes, there's a huge debate about what the propagator does for vanishing momentum, but that drops out of all observables.
How it corresponds to the Gribov-Zwanziger expression for the modification of the gluon propagator?
So once again, we have tested this actually for...
gluon propagator is modified due to these copies of Gribov copies in the form of Gribov-Zwanziger, where you have, instead of mass squared, you have something divided over p square. So for small p, this effectively this mass term rise.
Yeah. So this is a very technical question, which of course I haven't discussed here. We have tested this for, I mean, this is concerning a global closure of the gauge fixing in the infrared. And there are various versions. There's Gribov-Zwanziger, Kugo-Ojima. There is a solution which you actually see on the lattice where the propagator goes to a constant. And this drops out of all physics. So nothing I have discussed here in terms of observables does depend on it. And it's precisely for the reason that I looked at some momentum, at some dimensionless quantity here, because it's the dimensionless quantities that decide about the physics. But if you would plot the different solutions here for different closures of the gauge fixing, you wouldn't see a difference in the dressing function.
At net, you have gluon mass or gluon remains massless in infrared?
The gluon is gapped. And that is what you see in the dressing function. Okay, that's the reason why the dressing function goes to 0.
I see.
Okay, and we have tested it for, I mean, different Gribov-Zwanziger, Kugo-Ojima, and lattice type infrared closures of the gauge fixing. And as it should, it drops out.
If there are not questions, I have another topic for conversation. Okay. If there are not others. Let us imagine, I do not manage to draw formulas yet, but by on the language level. Let us imagine the statistical sum. You have trace exponent, in the exponent minus beta multiplied Hamiltonian, and chemical potential terms, right? Chemical potential operators or charges and Hamiltonian are very symmetrically enter in this expression. Just, you name, there is beta, and for chemical potential term, you have beta multiplied mu or just mu. It depends on the definition. So these expressions are very symmetric. with respect to Hamiltonian and the charges, Q square, for example. What's the reason why this expression is so difficult to calculate? Thing is that Hamiltonian for realistic systems is bounded from the below, right? You have background. Because of this, you can rise beta and so low temperature and statistical sum has sense, not diverges. But if you have density of states rising exponentially, as in extended particles, right? Extended particle strings or membranes and anything, a nuclear seal. If the density of states rise exponentially with respect to energy, then for some temperature, statistical sum becomes divergent. So you have some kind of phase transition. In QCD, we have exactly the same case. You have Hagedorn temperature, maximal temperature.
Okay, guys, I don't think this is the right time to go back to the whole formalism of quantum statistical mechanics. I think let's ask there's some concrete questions to be asked.
Question is, why charges, Q square or electric charge, is so difficult to calculate? We need to change imaginary chemical potential and then analytically continuation. So question is, why this is?
We use the past integral. We use the past integral formalism.
Maybe because charge is not restricted from below. So if there are states with negative charge, then with realistic chemical potential, statistical sum just will be divergent, not defined.
Okay, but I think it's because we use past integral formulation where time, so the Hamiltonian plays a special role in terms of time evolution, and the charge, non-zero chemical potential breaks time reversal symmetry.
Sure. So we can consider charges as a Hamiltonians, if you like, and try to make evolution with respect to this chemical potential. And this is the net. So we have in that, you have explicitly multi-Hamiltonian system. Every charge plays the role of Hamiltonian. They can be considered as evolution in the chemical potential direction.
Okay, I don't want to have a general discussion about the path integral and the partition function, but I propose to have go to Maria to have a concrete question about the talks. Maria?
Oh, there are many questions already. Okay.
Okay, shall I want to switch off on the, yes, hi. I would like to go back briefly to this nice plot that Jana was showing, this scaling or universal, almost universal relation between the chiral condensate and the chiral susceptibility. I think it was on page 15 of her talk. And in particular, I was curious about these coefficients that you call beta, the dependence on mu, because naively, I would expect that this plot should be universal in the scaling region. So should not be any mu dependence, in fact, because within this, I was naively, because in the scaling window, we can consider scaling variable, including mu, something like T minus the temperature minus T naught, pu k mu square, something like that. And then basically you have both chiral condensate, chiral susceptibility as a function of this scaling variable. And so you can just invert one. And so you have a universal scaling for, I think it's a very nice plot of a chiral susceptibility versus chiral condensate. Yeah, thank you. Page 15 was perfect. Page 15.
Yeah, sorry, I needed a moment to find the reference.
Very nice, very nice. Yes, yeah. This bit, because you see that indeed they fall very nicely on top of each other for any mu. And I really think that's a nice confirmation of scaling. I don't understand this beta I. I think they should be very close to 0. Is this true?
Well, I mean, you see that there's not a strong mu dependence, but there is a mu dependence. So they're not perfectly on top of each other. And I think if you would want to fit, you would see that that doesn't work very well if you just pretend there's absolutely no mu dependence. Also, there is no region why one should assume one is necessarily in the scaling region here.
Okay, so, but yeah, you agree then any mu dependence should come from scaling violation. So because if this was within scaling, there shouldn't be any mu dependence. Actually, you can even compute probably this curve from, you take this Fritjof parametrization in the paper with Engels, and then you have all this parametrization for the equation of state. So you can really have this curve exactly drawn. That would be nice.
Yes, one could consider that. I haven't done it though.
Okay, but then so you agree that indeed if we were exactly in the scaling window, then this beta I should be 0.
If we were exactly in the scaling region, we plot the stability as a function as a chiral constant.
Yeah.
I can very well imagine it, but I can't give you a real proof right now for that. So.
Okay, maybe we, let me repeat, repeat again the motivation for this, because both chiral susceptibility and chiral condensate are described by universal scaling function of the scaling variable T. Now, once we include chemical potential, either real or imaginary, for small chemical potential and within the scaling window, the scaling variable is just contains the chemical potential. It just describes the pseudocritical line. And so
and then it should cancel.
It just inverting one curve, and then it should be automatic that any universal function could be expressed of any other function described in terms of universal scaling functions. I think it's something that one may really try to compute once one has the parameterization.
If I can just throw in, Maria, I think you are completely right. I think Anja Bahn has his hand up. He probably wants to say the same because I recently discussed it with him.
Okay, good, thank you. And thank you, Jana, it was very interesting.
Yeah, it's enough. So just my question during your talk was, you don't need these beta i's, say, to compute kappa then, kappa 2. It's not related to the mu dependence of these particular curves.
What we need them for is to get this curves properly described and then to compute the maximum. So in some way they enter to describe, to determine the maximum of the chiral condensate for each mu. But they have a very small influence in the final result.
Okay. Yeah, Anja Bahn, you have your hand up still. Indeed, you want to say something similar?
Yeah, not about this, but I had another question about Jana's talk. That you showed that this the proxy for the actual width doesn't go large with chemical potential. So you plotted sigma rather than this delta T, and you showed that that doesn't grow with chemical potential, but you didn't want to make any strong comment. But I'm wondering about the, you also have chiral susceptibility at the crossover temperature for various chemical potentials, right? Where you don't need probably any extrapolation or any finite order polynomial to extrapolate somewhere, which is plotted exactly as negative mu square. So there is no, I mean, not probably in your plot, but you have results, right?
We, of course, have the results for imaginary chemical potential. The reason why I didn't want to make a strong claim here is because our error on the width grows with the extrapolation so much. Yeah, so yes, this is constant within the arrows, but at least here the arrows are large. So
no,
there is still room for growth.
Maybe I can finish my question. So my two questions are like, how did you extrapolate the sigma exactly to the real mu? And my second question was, I mean, when you don't see a increase in the chiral susceptibility along the mu direction, in the negative mu square, of course, but does is that curve somehow can be put with better confidence about the anything not being in the region mu less than 300 MeV or mu by T less than 3 or whatever, that region? I mean, whether that finding that chiral susceptibility doesn't increase with increasing mu B in the imaginary direction also. So does that tell you anything else or something more in the?
Well, I think the problem with this extrapolated quantity is always that the extrapolation is only guaranteed to be right as long as you don't hit any non-analyticity. So just because I don't see anything, it doesn't guarantee you that nothing is there. How we did this extrapolation is we calculated the point where the chiral condensate is 0.215 and the point where the chiral condensate is 0.355. We extrapolated those contours. They are in the paper if you want to see that plots. And then we took the difference at this as width, and because these curves lie so nicely on each other, that works fairly well, and it looks so constant.
How to the real mu, I was asking, because those measurement those calculations were at imaginary mu.
If we do the calculation at imaginary mu, but then we extrapolate to real mu. So what is plotted here is real mu.
Okay, thank you.
Okay, then Wolfgang.
Hello, can you hear me?
Yeah.
Okay, so I have a comment and a question to Jana again on this issue about plotting susceptibility over the chiral condensate. So I observed the same thing in strong coupling QCD at real baryon chemical potential. Concerning the comment of Maria on that this is maybe universal behavior, I have a question about this dependence on beta, because I rather observed that in the crossover region that this has a different behavior than at the critical point. So when you go towards the Robert-Weiss point, does your beta react on that? Because when I look at your black data or gray data, sorry, for 7 pi over 8, that looks that it deviates most from that curve. That is when you get closer to some criticality.
Yes.
Is that also what you observe, that beta gets kind of different from the crossover region when you reach the Robert-Weiss transition?
I'm sorry, I can't tell you the values we fitted for beta on the top of my head, because I only did them in the individual fits and never made a full analysis of them, actually, because I didn't consider them that interesting. You're teaching me that I should look at them.
So what I suggest is that maybe there is a universal curve, but in the crossover region it might be a little bit different.
It's perfectly possible. So I don't think that we have such a good scaling here that one should just forget about the mu dependence. And we really needed to get a proper fit here. So it gets reduced by fitting everything in terms of the chiral condensate, but it doesn't vanish.
A strong coupling, maybe the mu dependence factorizes in a certain way that it's easier to see. that the rate that the Wolfgang?
May I say something here? So when you look, of course, at the chiral susceptibility, they are not the same coefficients. You check out the fugacity coefficients in this way. So at least in a finite volume where you can do this analysis, there should be some small dependence in coarse origin.
Yeah.
Maybe I ask my question now again since Vladimir is back. So I had a question about the remark that Jishnu made that the temperature of the critical endpoint lies below the transition temperature in the chiral limit. And Fritjof said that there is a plot in your talk that could address this. So maybe you can show your slides again.
Yeah, give me a second. I mean, it's naturally to expect, although of course it's not a proof. Yeah.
Yeah, this one.
This one would work. So the transition temperature you expect to be here. Oh well, this the second order phase transition, which is 04, is over here. The critical point, critical point you expect to be lower because of the curvature of the phase diagram, and the curvature we know. Yeah. So also in many models, at least in the models, and also in the scaling regime, we know that the curvature of the of this line over here, this really skinny line, is so it goes down with temperature, at least very close to this, to the critical point. How it behaves later on, it's probably not really known, especially in QCD, but it is reasonable to expect that the critical endpoint will be also at lower temperatures. So this is Fritjof argument. I mean, probably Fritjof would.
So actually,
as I said, it's not my argument. This form of the phase diagram comes out of all model calculations, and it comes from the mean field analysis of the tricritical behavior from Hatta and Ikeda. So it's very reasonable to assume that it is this way.
Mm-hmm. Okay.
So actually, Anirban shared these references in the chat, so you can look at them.
Yeah. Okay, I hadn't seen it before, so it's interesting. Okay, Christian has a question.
Yeah, can you hear me?
Yes.
Okay, this is a question to Vladimir. Your calculation of the radius of convergence is actually from the singularity in the complex plane. So I'm curious, you could simply determine now the chemical potential where it pinches the real axis, right? So you can predict the critical point.
Yes and no. I would say you shouldn't trust it. This would be an overstretch. So okay, so let me like briefly comment on the mean field or how this happens in mean field at least, so that you would understand why it would be an overstretch. Although I was telling you that it is continuously connected, the way it's continuously connected is not very trivial. So let's look at this Landau functional here. So we have the temperature, and at O4, this this parameter goes to 0. Okay. So far so good. And this is the behavior I'm trying to essentially capture. And this equation over here captures this behavior. Okay. What it doesn't capture is when the phi to the fourth term coefficient goes to 0. And this defines the location of the tricritical point, and it also affects the location of the critical endpoint. Okay, I just set it to 1 here because I'm not interested in its behavior. I just set it to 1. And however, if I wouldn't set it to 1, it would enter into this Z0 parameter, which you have on the lattice. Okay, so it would enter into the parameterization over here, like 1 over this, let's call it lambda, 1 over lambda. Okay, and what it means essentially that my scaling variable will have some non-trivial singular behavior close to the critical endpoint or the tri-critical point where this coefficient vanishes. And then I would have to redo my analysis by including the high order corrections over here. Okay, nevertheless, given that, it is still true that if you consider, for example, this mean field calculation over here, which I showed in the very beginning, if you define this radius of convergence in the crossover region, okay, you can probably, extrapolate it a little further, and it might tell you at least approximate location of the critical endpoint. As far as the reality of when my line will cross the real axis, it will never do that. It will never cross the real axis. So that's the short question to you. Short answer to your question.
Okay, thank you.
Okay, Fritjof?
Yeah, at this point, I would also maybe ask something. So Vladi, when it comes to putting in physical numbers, then you use these non-universal parameters, Z0 and so on. But when you end up with a chemical potential that is quite far away from zero, don't you also have to reconsider the parametrization of Z, which is after all only a leading order Taylor expansion of the renormalized trajectory in the vicinity?
So I would say that the value of chemical potential probably is not as important as the value of Z itself. And Z is not large, yeah, so Z is of order of 1. But I take your point. Indeed, probably you have to consider high order corrections, especially here. Yes, if the high, but even kappa 4 wouldn't matter if I would take the correction over here. Yeah. So, but let me put it in a little bit different way. So, of course, you can say, I mean, to begin with, you can say that maybe QCD is not in the scaling regime or for dynamics for the physical pi mass. And this is why I'm getting this high values in the chemical potential as well. Well, I can tell you the following. Well, it definitely is for the small pi mass. And for example, maybe you can look at this green curve and say that indeed this would, how QCD would behave if I would consider the pi mass, which is 16 times smaller than the physical one. And the rest of these curves you can consider as a model. Well, I mean, at least this model is based on something. It's not just a quark-meson model or something. At least it is based on the some information about the actual analytical structure in QCD. Yeah, so it's an extrapolation to higher values of the pi mass. I mean, at least you can treat it like this. Okay, so it probably wouldn't give you the exact number in for larger masses, but it would give you, some estimate of the radius of convergence. So Christian, just to return to your question very quickly. So I'm solving this equation, Z equals to ZC, and ZC is a complex number. And this is why I will always get complex values for the chemical potential.
Can someone quickly say where the hand raising tool is on the Zoom?
You click on participants and then in the new box on the bottom.
Wow.
I have just more there, and mute all, lower all hands.
I think because you're a host.
Jan, so Jan was asking.
Yeah, I also don't have it.
Yeah.
So as a host, we don't have it, obviously.
As a host, we don't have it, that's why. Yeah.
Because we can mute everybody, so we don't need the hand raise. I don't know, okay. So, okay, I'm not completely stupid. I was getting worried because I didn't see.
Once again, about chemical potential, if you please.
Okay, yes.
I think if you suppose some analytical form of the dependence, then you probably can uniquely make analytical continuation. Let us find such proper analytical forms based on the solvable models. How it works? We can take some solvable models starting from oscillator and more difficult, and try, and we have explicit form for the imaginary chemical potential as well as for real. And try to calculate numerically the imaginary part and try then to reconstruct the real one. Obviously, we have not polynomial function for the exponent extrapolation. Something exponents we have. From one side, some oscillating exponents, Fourier expansion, if you like. On the right-hand side, some decaying exponents. Probably thing is how to guess proper ansatz for the dependence on the chemical potential and then try to fix uniquely such a function. Maybe this is the way to input some a priori information. And then maybe extrapolation will be unique and proved, if you like, because you may be wrong, but you do not know. You obtain something sensible, and you then will believe. But similarly, another person makes his expression for the real chemical potential. And you will have, if you do not have experimental data, define which is more correct, which answer is proper, because there are arbitrariness, big arbitrariness in this extrapolation.
Yeah, it's more like a common, but yeah, I mean, there are many, I mean, in simple models, the mu dependence comes always as a, say, a cosh or something, or like an vorticity expansion, and in hadron resonance gas, it appears in a very obvious way as well. But once you get out of that, then you have to, well, then you can do attempt as a Taylor series or on a Padé approximation. But of course, it's very hard to know what it's, I mean, in the hadronic phase, it comes with all the baryons, for instance. So you know, you have an idea what it looks like, but not an exact form, say. Yeah. Actually, yeah, somebody made a remark about that you need 30 orders to get it right. I think it was Vladimir or something. Actually, Guy Moore had an old paper about this in a simple model doing it. And I think maybe you were referring to that paper.
So this was a calculation done by myself quite some time ago, but I don't think we ever published it. But it's just this plot.
Yeah. So Guy had a paper about this.
I think there's a paper by Bernd Jochen Schäfer and Fridtjof Karsch and others about this, where I mean, the statement is you may need a lot of coefficients, but you don't know.
That's correct. I think we came up with 26 order, but I think that is also a question, what goal you have. I think when you aim at, say, 20% accuracy, you can get away with much less.
You may get away with much less.
Yes, yes.
Yeah, that, I mean, of course, is the statement about the uniqueness. I mean, the statement is if you know the function, you know the function. If not, you don't know. Right?
Maybe this is a good point to raise a question then that, so some questions were submitted before the session. And a few questions were quite similar, namely in what do we actually know about first order phase transition lines at higher chemical potential, or about the existence of a critical endpoint and so on. So, so maybe people who feel they know something can state something which is kind of known with a certain, a certainty more than, so say 50% or aim a little bit higher?
Well, I think everything that is known there is based on model calculations.
Yeah.
I think right now we simply don't know. That's what makes also the extrapolations hard. And you mentioned it already, Gert. I mean, of course, we have other excitations there. And I mean, this is a problem while you also know very well if you have reconstructions, you try to guess structures which are hidden in potentially exponentially suppressed features of your data. And since we are all talking about data, either I mean, from simulations or from numerical computations with systematic errors, I mean, these, let's call it exponentially suppressed features are very hard to guess. And it's also, in my opinion, in Vladimir's talk, if I mean, you have non-universal and universal parts, if the relative coefficients, which are actually non-universal properties, are large or small, depending on this, you have a chance or not. Right, so if you're looking at, I mean, in my opinion, there are also model computations. Of course, the one I have in mind is an RG computation by Jens Braun and Bertram Klein. So you may have to go to very low pion masses to see criticality. That actually was one of the slides I had, and I only flashed it. In our chiral limit computation, we didn't see critical scaling up to pion masses of 25 MeV.
That is a point where I wanted to talk about with you also. I don't know, we can do other things first.
Yeah, sure.
But let me tell you something. I mean, you should be excited about this point. It's also a critical endpoint, okay? It's just at the complex chemical potential. But why not? We are theorists, right?
No, I completely agree. I like this a lot, as you know. And actually, I mean, that's one of the things how you can get track down the structure. If you have information about the structure of your function in the complex plane, I mean, you can restrict it quite severely.
I have a question which might be related. It had to do with someone's talk. Jishnu's talk again, yeah. So you said that at, say, pion mass of 40 MeV, the Robert-Weiss transition is still Z2, I think. And so am I correct in thinking that if the Robert-Weiss endpoint transition is still not a tricritical point, but still second order, that means that for sure the transition on the real at 0 mu is also still crossover then? Is that correct statement?
You mean
so? Usually, in the sense that usually we connect the line, the thermal transition line, to the Robert-Weiss line, and if everything is first order, it's nice as a tricritical point. But if the endpoint is still second order, then the transition, the thermal transition, will still be crossover for sure.
Yeah, that is
so. So my question is it easier to actually study the critical endpoint and the Robert-Weiss endpoint and determine for which pion mass it turns into a tricritical point? Is that an easier calculation to do than to study the thermal transition at 0 mu and see for how low pion masses you have to go to find the first order transition there?
You mean first order chiral transition or first order triple point?
Yeah, it's a triple point. There are 3 phases, 3 first order lines come together. Yeah, triple point. Yeah. So just numerically say, is it easier to study the properties of the Robert-Weiss endpoint than it is to study the thermal transitions at 0 mu?
That was the idea of Jishnu's 3-dimensional phase diagram.
Can I share my slide if you?
Yes, yeah.
Just a minute.
Yeah, so this plot we know very well.
Yeah, so this plot is telling you that when you are in the Roberge-Weiss plane, the critical mass is larger than at 0 mu.
Exactly, yeah.
So that tells you, in principle, it is easier to do it in the Roberge-Weiss plane because you don't have to go to such a small pion mass.
That's right. And also the transition is, I mean, even when it's not a triple point, it's definitely a second order point, so that it's easier to look. It's always a transition.
Yes. So, yeah. But the point is, even there, you didn't find a first order transition.
First order, yeah. Yeah, so that was my question. So why not put a limit on the pion mass in this plane? But you have not managed to find the transition there.
No, that's what Gishno did. He said that the current limit is a pion mass of 40 MeV.
Yeah, but it was still a second order transition.
And it's still second order.
Yeah. Okay, so that means at 0 mu you have to for sure go less than 40 MeV. So it's very, very low. Yeah. Sure.
Life is tough.
I had a question to Maxime, actually, myself. And it was partly because I didn't pay attention for a few minutes and then it happened already. In the Timbo decomposition, I read in the abstract that you found that, in fact, you don't need the number of symbols, the number of relevant symbols doesn't scale with the volume. Is that what you said?
Well, it depends on it depends on the formulation, actually. So that even for the same physical model, when we have some freedom in formulation of path integral, then sometimes we can have number of symbols which will scale linearly with lattice size. Or in some special cases, if we tune this non-physical degrees of freedom, we can actually have just fixed number of symbols which does not grow with lattice size, or we can have just one symbol, which fills the whole integral for partition function in any case.
And of course, you only know this a posteriori, I guess.
Yeah, unfortunately, we can do it only if you have. Well, not completely, I would say, because okay, at half filling, when we have sampling with hybrid Monte Carlo, we notice it a posteriori. A way of half filling, we do it like this: we sample initial starting point for search process somewhere away of symbol. So that in principle we do not need exact sampling over symbol with sign problem and so on. But yes, still some kind of sampling we need. Mm-hmm. Yeah, that's all.
Okay, thanks. Yeah, thanks. Okay, are there any further questions?
I have a question to the Ian and then topic. Not short, unfortunately. For the Ian, again, functional renormalization group. By order parameters, we identify phase transition points and so on. But the concrete question in the Glue dynamics, can you indicate the value of fine structure constant in the infrared?
I mean, this is for me not a meaningful question because in the infrared, I mean, of course, the different definitions of the fine structure constant are two-loop universal, but in the infrared, you have many different versions of it, and they just simply look differently.
Scheme dependence. surely.
No, it's not scheme dependent. I mean, of course, we have vertex couplings, and some are going to zero, some are actually turning negative, right? So it is no meaningful question. So what you can say is meaningful definitions in terms of scattering couplings that tell you how gluons, for example, scatter or quarks, they all go to zero. The theory decouples, or if you wish, the glue dynamics decouples for small scales, which is just the mass gap in QCD.
Okay, but the critical point of the coupling constant at which beta function is zero is qualitatively crucial. Its exact value of the critical point is dependent. But the existence of critical point is universal.
Look, the couplings turn to zero, they grow, and then at small momenta they decay again, right? I mean, the concept of a beta function, as we are, known to use it in perturbation theory, simply does not make sense there. And if you want to look at some critical coupling in terms of glue dynamic, you will have a hard time. You have to define this differently. Of course, you can do it in a way like the interaction measure is defined on the lattice, and we also use it. That would be a decent coupling. But there you also see this is a measure which rises and then drops to zero. Right? And if you want to get some beta function out of it, you would say it's a multi-valued function.
Let me make slightly more concrete the question. In the perturbation theory, you have first loop and second loop contributions in beta function reparameterization invariant in the critical dimension, right? You can take the scheme, not explicitly constructible in every perturbation level, but their scheme where all higher contributions perturbatively is zero. You just construct by explicit form of the coefficients that parameterization perturbatively. But if you somehow know non-perturbative addition to the beta function, which will be a reparameterization invariant, but non-perturbative, then the critical point will have universal sense, I think. It says some.
It's a nice concept. I mean, it works if you have something like supersymmetric theories like Seiberg-Witten. It simply does not work here. That's my opinion about it. More I cannot say. And in a way, our couplings are, let's call it, I mean, they have a physical significance. As I said, they tell us whether the glue dynamics is still around for small momentum values or not. And what we see is, of course, they decouple. So more I cannot say. I mean, I know that these couplings are around, and I've used them myself in supersymmetric theories. And so if you wish, I know a bit what I'm talking about here. This concept does not make sense. Or let's put it like this, I have not been able to make sense out of it. And I like it.
Okay, then I will save time for the second more general.
I just want to suggest, basically, we had like 55 minutes of discussion now. So it's dinner time in many countries, from the UK and then going east. Roman, shall we close the session?
Yeah, if no more points to be discussed, yeah, so we can close it. Yeah, okay. Gert, thanks a lot for doing very nice job of chairing the session and being discussion leader.